Myself, Dr. Sayanti Chatterjee, Associate Professor of Institute of Aeronautical Engineering, Hyderabad, from EEE Department. Today I am going to tell about the Lorentz Force and its application. So, Lorentz Force and its application, before starting, we have to know where we can use the Lorentz Force. So, Lorentz Force we can use in the magnetic field. This topic is a combination of the electric field as well as the magnetic field. So, first we will discuss about the Lorentz force. We can write at F is equal to Q V cross B. Actually, this is the primary definition of the Lorentz force. But in this topic, we will discuss more in depth about the Lorentz force. So, when there is a magnetic field, can exert a force on electric charge only if it is moving. If there is a fixed charge, it will not exert any force on it. So, magnetic fields can exert a force on electric charge only if it is moving, just as a moving charge produces a magnetic field. Like if we have, before starting, we have to understand what is a magnet. So, magnet is basically two types. One is the permanent magnet and electromagnet. So, when there is a magnet, it will, if any magnetic material is, if it is a magnet, any magnetic material is near to it, it will attract with it. So, the area up to which it can attract or repel any other magnet or any other magnetic material is known as the magnetic field. So, magnetic field, if we keep any one of the electrical charge in the magnetic field, it will also experience a force. So, the experiences force, but if the charge is only moving charge is nothing but the current. So, if there is any current carrying conductor, it will only experience the force. But if any charged particle is there, it will, in an open charge thing is there, it will not experience any force. So, a moving charge produces a magnetic field. So, magnet is basically two types. One is the permanent magnet, another one is the electromagnet. So, today we will discuss about this magnetic field. So, the force increases with the both an increase in charge and the magnetic field strength. So, as we discussed that force depends on the electrical charge and the magnetic field. So, if we increase the magnetic field, the force will increase. If we increase the charge amount, it will also increase. So, we are giving one simple example of a DC motor. What happened in the DC motor? We have two poles in the stator, 2 poles, 4 poles, 6 poles in the stators, and are giving the connections. So, what will happen? One north pole and one south pole will set up in the poles. Now, we are keeping one armature inside the rotor portion. Now, so this will create some magnetic field and this will create some electric field. So, as a result, here, if we increase the current in the pole, the magnetic field will increase. So, that we can tell magnetic field will increase means what will happen? That it will get the more force. Similarly, if we increase the current in the armature, it will also increase the force. So, the force depends on the two things. One is the increase in charge or increase in current and the magnetic field strength. The force is greater when the charge of the higher velocities. Why? Because we know that the force only depends on the moving particles, not the stationary particles. So moving particles means it should have some velocity. So force is always depends on the velocity. If velocity is more, it will exert more force. So if we combine these two things, we can find the Lorentz force. The magnetic force, however, acts as the perpendicular to the velocity. This force can never produce work on the charge and can impart it if any kinetic energy is there. So force can be defined as force is equal to Q V cross B. Where what is the Q? Q is nothing but the electric charge, but it should be the moving charge, not the stationary charge. Then what is the V? As this is a moving charge, so V is the velocity of the charge. And what is B? B is the flux density. So we can write F is equal to Q V cross B. And the magnetic force is given by, so what is this? We got it. So we can write it Q V B sin theta. This is a cross product. Now what is the theta? Theta is nothing but the angle between the V and B. Nothing but the angle between V and B. So as we discussed, Q is the charge, V is the velocity, and B is the magnetic field, or we can tell this is the magnetic flux density. So because magnetic field H is equal nothing but the mu into B. So thus it always acts out of the plane and does not contribute to any work done on the charge. It can merely change the direction of the velocity. This type of force cannot change the velocity of the and cannot change the direction of the charge. It can change the this force is used to change the magnitude of the velocity of the charged particle, because the direction can only be determined by the Fleming's right hand rule. What is the Fleming's right hand rule? If we keep our right hand 3 fingers, first finger, middle finger and the thumb in the 90-degree perpendicular to each other, and if the first finger gives the direction of the field means B, and the thumb gives the direction of the V, then middle finger will give the direction of the force. Now we will recall about the force on the due to the electric field. We know according to the Coulomb's law, force is equal to Q1 Q2 by 4 pi epsilon 0 r square. This is the force if there are two charged particles. The force acting on it depends on Q1 Q2 by 4 pi epsilon 0 r square. So if we again we know E is equal to, or we can write if there are two charges Q and Q1 by 4 pi epsilon 0 r square. Now what is the intensity? Intensity means the work done to bring one unit charge from one place to another place. The force required to bring one unit charge from one place to another place. So one charge is unity. So it will be Q by 4 pi epsilon r square. So what is the relation between F and Q? F is only for the Q1 charge and E is for the single charge. So we can write force is equal to Q into E. So force is equal to Q into E, or we can write Q1 into E. So this is the force due to the electric field on a charge is built into its definition. So this is the force due to the electric field. So if we combine these two equations, we got the force due to the static electric field is equal to Fe is equal to Q into E. Similarly, for the magnetic field, we can get Fm is equal to Q P cross B. So, if we combine together, we got F equals to Fe plus Fm. Fe plus Fm. So, Fe is equal to Q into E, Fm is equal to QV cross B. If we combine together, we will get the Lorentz force. So, this chapter is about the Lorentz force. Now, force on the current element due to the magnetic field. Let us assume a long conductor L which is partitioned into the number of parts allowing current I. Each part of the conductor you are taking as the length is dl. Total length is L and the small part is the dl. So, if this is a conductor, we are dividing it into the small part, equal part, and all part is dl. If I current is flowing in the total conductor in each segment, the current is I dl. Now, from the previous equation, we know if there is any magnetic field, the magnetic force dF is equal to dq V cross B. For a small infinite, this is a dl, this is a small portion, for the infinite is small portion, dF is equal to dq V cross B. So, what is V? V is nothing but what is the velocity? Velocity, or we can write velocity is equal to length by time. So, dl by dt, the time taken to go the dl length for the charge. So, again we can write df is equal to dq dl by dt cross b. Now, from the previous unit 1, we know dq is equal to rho v into dv. What is rho v? Rho v is nothing but the volume charge density. So, rho v is nothing but the volume charge density. So, we can write rho v is equal to rho v dv. Here this v, this capital V, this V is the small v is the volume. Capital V is the velocity, the capital V is the velocity and the small v is the volume. So, we can write rho v dv V cross B, or we can write df is equal to dq dl by dt cross B. Again, we know that rho v into v, if we take rho v into v, is nothing but the flux current density. We know from the previous chapter J is equal to rho v into v, where v is the drift velocity of the electron. We have discussed this. So, J is equal to rho v into v. So, J cross B dv. So, this is the another equation we got. So, first equation we got df is equal to dq v cross B. This is our first definition. Df is equal to dq v cross B. What is the second one? Df is equal to dq dl by dt cross B. What is the third one? Third one we got df is equal to rho v dv v cross B. This is our third equation. What is the fourth equation? df is equal to j cross B into dv. J cross B into dv. Again we can write it as this is the V. We can write as J into dA cross B JDA means we have under J into A, we have the L, because volume is equal to, what is the volume? Volume is nothing but the area into length. So we can write the dV as A. dV can be written as A into dl. J into dV can be written as I into dl. So I into dl cross B. So the same equation we can write in the different manner. And if we integrate the equation, we will get, what is I cross B? I B dl sine theta. And if we integrate it over the time, we will get the force is equal to BIL sine theta. So force on a current, so we got for a charge, it is Q V cross B. But when we are discussing about the current, it became force is equal to BIL sine theta. So force on a current carrying conductor depends on the flux density, current, the length of the conductor, and the angle between I and L. So now we will discuss that the force on a straight long current carrying conductor due to the magnetic field. So here we are thinking about a long conductor where the current I is flowing, and there are some charge D. So the velocity of the charges of the conductor is taken as the V. What is V? As current is flowing means there is the flow of charge, and flow of charge means there is some velocity. So this velocity is taken as the V. So the force experienced by the current carrying conductor, we know dF is equal to dQ V cross B. So again we can write dF is equal to dQ dL by dt cross B as we discussed earlier, and dQ by dt is nothing but the di. So we can write dQ by dt is equal to di dl cross B. So dF is equal to di dl cross B. We can write it as the di dl v sin theta. If we integrate it two times, once with respect to dl, once with respect to I, we will get force is equal to BIL sin theta. So force on a straight long current carrying conductor due to magnetic field, we can prove in the two types. One I have discussed in the previous slides, and now we have discussed the another method. So we got force on the straight current carrying conductor F is equal to BIL sin theta. Now we will discuss what will happen if there are two long conductors placed in the magnetic field. Previously we have discussed about the only one conductor. Now what will happen if there are two long conductors are there? So let us consider two straight parallel current carrying conductors L separated by a distance A, distance D, and what is the H? H is nothing but the I by 2 pi R. When there is a current carrying conductor, the magnetic field intensity in the circular way is nothing but the H is equal to I by 2 pi D. This is the Ampere circuital law. So from the Ampere circuital law, we can write H is equal to I1 2 pi D. So what is B? B is nothing but the, we know what is B? B is equal to mu naught into H in the air. If the two conductors are in the air, we can write B equals to mu naught into H. So H value we got I1 by 2 pi d. So what is the force experienced by the conductor Q due to P? So it is F1 is equal to B I2L. So if it is the 90 degree, we are taking it the 90 degree angle between this I and L. I and L, we are taking 90 degrees. So force is equal to B I2L. The force on the first conductor due to the second one. So current is the second one and force in the first one. So F B I L, B I to L. Now what is B? B is nothing but the mu naught I1 by 2 pi d. So B is nothing but the mu naught I1 by 2 pi d into I2 into L. So this is the force on the first conductor due to the second one. Similarly, we can write F2 is equal to mu naught I1 I2 by L by 2D. So we can get that the both answer, this F1 and F2, both are the same. So what is the force per unit length? Force per unit length is mu naught I1 I2 by 2 pi d. So this is a very important equation. If there are two current carrying conductors parallel to each other, if there are two current carrying conductors who are parallel to each other is situated in any place, we can write F by L is equal to mu naught I1 I2 by 2 pi d. What is d? D is nothing but the distance between the two current carrying conductors. Next, we will discuss about the magnetic potential. So similarly to the electrical potential, the magnetic potential can be defined as the work done to bring one unit north pole. In the place of unit positive charge, we will take unit north pole from one place to another place, from one side to another side. That is the magnetic potential. So magnetic potential can be defined into the two parts. One is the scalar potential, another one is the vector potential. So magnetic potential is the property of the certain substances or phenomena that gives rise to the magnetic field. Like due to the electric potential, current flows, we know. Similarly, magnetic potential is the property of the certain substances or phenomena that gives rise to the magnetic field, which causes to generate the magnetic field. So what is the scalar potential? Magnetic scalar potential is written by psi. Magnetic potential is written by psi is a quantity in classical electrical magnetism and it is similar to the electrical potential. So magnetic scalar potential is similar to the electrical potential. So in the electric potential, we know E is equal to minus dV by dr, or we can write E is equal to minus grad V. What is grad? Grad is nothing but the d by dr. So similarly, if we go for the magnetic potential, then H is equal to minus grad Vm, minus grad Vm. Now if we take the grad in the both side, we can write grad cross H is equal to minus of grad cross grad into Vm, grad into Vm. So divergence of any vector, as H is a constant term, so grad cross H is equal to 0. And also we can write, actually we know the curl of divergence of any vector is 0. Curl of divergence of any vector is 0. That means grad cross grad Vm is equal to 0. The curl means cross product of any divergence is equal to 0. Again, we know grad cross H is equal to J. So, from the above equation, we can write J equals to 0. J is nothing but the field intensity. J equals to 0. We know from the electrostatics E dot dl is equal to V, because V is equal to minus dV by dr is equal to again E into dl. Similarly, we can write integration of H dl is equal to Vm. What is Vm? Vm is nothing but the magnetic potential. Then again, according to the Ampere circuital law, in a closed path, there will come a term in a closed path, integration of H dl equals to I. So we can write, comparing these two equations, Vm equals to I. So the units of the scalar magnetic potential is ampere. Generally, the unit of the potential is volt, but here we can use the unit is ampere. So after this, it will come the vector magnetic potential. Vector magnetic potential is the property of the magnetic field only. Magnetic vector potential A is the vector quantity defined so that the curl is equals to the magnetic field grad cross A equals to B. We know that the divergence of the magnetic field density over a closed surface is always 0. So grad B equals to 0, and divergence of the curl is always grad cross A equals to 0. So if we compare the two equations, we will get B is equal to grad cross A, mu into H. In the place of A, we are writing mu. So it is grad cross A. H is equal to grad cross A by mu. So B is equal to, we got grad cross A. And what is B? B is equal to mu H is equal to grad cross A. So what is H? H is equal to grad cross A by mu. And from here we can write grad square A is equal to mu J. And grad square A, if we are not taking the sign, we will get minus grad square A is equal to minus mu G. So this is known as the vector potential. And from the electrostatics, we know dV is equal to dq by 4 pi epsilon. And so from the, similarly we can write dA is equal to, in the place of Q we can write IDL, mu IDL, because H is equal to I into DL from the Ampere circuital law. So we can write A is equal to integration of mu IDL by 4 pi R. So this is the equation of this is the form of the magnetic potential. Next we will discuss about the permanent magnet. Permanent magnet are the magnet which we can get from our nature. Permanent magnets are the one which readily available in the nature, from the bar and the horseshoe shape. It may be like the bar, North Pole and South Pole. Otherwise, it is like a horseshoe shape, North Pole and South Pole. Permanent magnets, irrespective of supply, always exhibits the magnetic property. So for the normal magnet, we no need of any external source or external current or anything. It will always show the permanent magnetic property. Permanent magnet always develops a constant magnetic field. So whenever as the field strength are constant, it will show always a permanent magnetic field. The strength of the permanent magnet measured in their cohesive force. Cohesive means how much attractive or repulsive force is there. It depends on this. And again we can use the Coulomb's law here. F is equal to m1 m2 by 4 pi mu r square. We can write it like k m1 m2 by r square, or m1 m2 is the force between the two things. Next we can discuss about the permanent magnet with the high cohesive force have the long life. If the magnet is more cohesive force, its life is long. Life is long means we can use it for the long time. Permanent magnet got the disadvantage of the aging effect. If the permanent magnet, as it is the natural thing we are getting from the mines and the other parts, it has the aging problem. So whenever it is going in the long run, it may got rusted. Some problem will come. So permanent magnet got the disadvantage of the aging effect. And permanent magnet are used in the application when there is a required to develop the constant field. We can use the PMDC, permanent magnet DC motor, and we can use it, as I told, there are two types of shape are there. One is the bar, one is the North Pole and South Pole, another one is the North Horseshoe. And next we will discuss about the electromagnet. Electromagnet, as per the permanent magnet, we will also discuss about the electromagnet. Electromagnet we can use in the electromagnet we can use on a iron or silicon steel. If we give some solenoid, we can get the electromagnet. So if there is a bar, we are giving some conductor here, and if we connect with the source, so one end will be the North Pole, another will be the South Pole. We can get the example of any machine in the stator part. Electromagnet is again two types. One is called the solenoid and another one is known as the toroid. So what is the difference between the solenoid and toroid? Solenoid means we are getting one bar, iron bar, and we are keeping the conductor, we are making one solenoid. In the solenoid, the two ends are not connected together. One will be North Pole, another will be the South Pole. They are the open-ended. But in the case of the toroid, what will happen? We are taking a circular path or disc, we are giving the connection on it, and this is a toroid. So in the toroid, the two ends are connected together. If we remove any portion, it will behave like a solenoid. So we can tell permanent magnet is basically two types, butt type and horseshoe type. But the electromagnet is two types. One is called the solenoid and toroid. So in our today's discussion, we have discussed about the magnetic field. Then we discussed about the force on the magnetic field. We discussed about the Lorentz force. In the Lorentz force has the two components, force due to the electric field plus force due to the magnetic field. And we got the equation F is equal to QE plus QV cross B. Then we have discussed about the force on a current element, and it is comes F is equal to BIL sin theta. Then we discussed about the two long conductors and the force came parallel conductors. Our current is I1 and I2, and we got force is equal to mu I1 I2 by 2 pi d, where d is the distance between them. Then we discussed about the permanent magnet and electromagnet. So this is my today's topic, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.